back to Beyond the Patterns. Today I have the huge pleasure to announce Sukyoung Won. She is a researcher currently at CalTech, and she is interested in nanoscale and microscale robots. And so she is using actually magnetic nanoparticles and polymers to construct really tiny robots. And they're not just nanoparticles, they really develop locomotion within magnetic fields. So I think she has super exciting things to show. I can tell you it's definitely worth watching, and I have the huge pleasure that she is here with her presentation entitled Polymer Composite Engineering for Microrobot Swarm Intelligence. Sukyoung, so glad that you're here, and the stage is yours.
Thank you so much, hello everyone, and thank you again for the kind invitation. And I also again truly appreciate the opportunity to present my results today. Before I introduce my results, I'm gonna introduce what is the polymers, because you do not usually your research area is not a polymer science and engineering, so. Polymers are basically long-chain molecules composed of the repeating units of the monomers. Due to this unique structure and physical properties, polymers and their inorganic composites has a lot of applications from the industry to the flexible electronics, biomedicine, and the soft robotics. So. In this talk, I'm going to introduce my research area on the programming the magnetic polymer composites for the microrobot Some intelligence. Some intelligence refers to the collective behavior of the multiple agents working together to achieve the complex task that a single agent cannot do alone. So in nature, we can see this phenomena in bird, fishes, and swarms. Inspired by these biological systems, some robotics aim to replicate these self-organism systems, and this approach has a lot of potential in the various applications, such as the making wireless networks and navigation and helping in factories, and even for the microsurgery and deliver of the nanomedicine inside the robot, but in the human body. Some intelligence has some key components. The most important thing is the local communication between the agent. Each agent can interact with the nearby agent, and by these local communications, the multiple agents can work together, organize to adapt in new situation and respond to change in the environment. Because of this collective behavior, the agent swarms can complete a task, even if some agent fail to come to the mission completion. The remaining agents keep working together to finish the missions by I call the bird tolerance. And to control the robot, some robots, the microscopic robots, typically use the inbuilt sensors inside the robot body. However, when the robot size decreases, it became difficult to integrate sensors and also batteries inside the robot's body. So instead, these small-scale robots rely on the materials that respond to external stimuli like light, magnetic field, or ultrasound. Particularly, magnetic robots can be remotely controlled in the micro-scale environment where manual control is not feasible. So by adjusting the direction and the magnitude of the applied magnetic field, we can precisely control the motion and the direction of these micro-robot swarms. This magnetic actuation is basically induced by the magnetization of these magnetic materials in the robot body. The magnetic dipole moment within the materials tend to align with the direction of the external magnetic field. So this magnetization from the moment alignment generate the magnetic torque applied to the microrobots. When we apply the rotating magnetic field, this dipole moment continuously align to the direction of the rotating magnetic field. So we can demonstrate the rotational mode of the robots, such as the corkscrewing, pivoting, rolling, or the other rotational motions. To this realize magnetic swarm intelligence, we need to think about that magnetic interactive energy, because the microrobots are positioned very closely to each other. Magnetic interactive energy increases rapidly when we see this equation showing an inversely cubic relationship with a dipole distance. Due to this high interactive energy, robots may assembled unintentionally, and this aggregation make the difficulty in the control of the desired motion or prediction of the trajectory of the robots. So to achieve the magnetic swarm intelligence, we need to implement the key components. First, the important thing is that local communication by the magnetic interaction. The robots is require for the controlling magnetic assembly and disassembly, and also based on this local magnetic interaction, the robots can show the self-organization with a reconfigurable swarm behavior through the multimodal actuation. And last one is for the environmental adaptability. These robots require high-speed actuation while maintaining the steering stability even at a high-speed actuation. So we can ask, what if we can control the distance of the magnetic particles by processing the polymers and magnetic particle composites? This enhances the inter-robot magnetic communication, enabling more precision and some controls. One possible approach is to modify the spatial distribution of the magnetic particles. For example, we can adjust the particle dispersion inside the robot body or apply the polymer coating, particle coating onto the robot surface. According to this magnetic interactive energy equation, this decrease in the particle distance drastically increase the magnetic attraction. That means the surface-coated magnetic particles can enhance the inter-robot interactions and promote the self-assembly between the multiple robots. And also, beside the spatial distribution, we can also consider the magnetic properties of the particles, such as the soft magnetic or hard magnetic properties. This magnetic anisotropic profiles in the robot allows the programmability of the assembly directions. So the first introduction is that the magnetic nanoparticles are uniformly distributed on the nanoscale in the polymer and the composites to achieve this independent motion of the multiple magnetic robots. This can minimize interruption between from the magnetic force between the microrobots. However, The nanoparticle dispersion is challenging due to their high surface area volume ratio and their closer interparticle spacing compared to the microparticles at a given concentration. Additionally, these nanoparticles has a high diffusion coefficient, meaning that they move easily within the composites. As a result, they exhibit a stronger interparticle interaction, leading to particle aggregation, and it could result in the negative impact on the robot performance. Additionally, we require high nanoparticle concentration to obtain the enough magnetization and the actuation. However, as we can see in this graph, the decrease the interparticle distance and promote the nanoparticle aggregation. So we implement the rapid precipitation method for the achieving the distributive mixing of these magnetic nanoparticles. First, the polyurethane and the nanoparticles were mixed in a good solvent, which expand the polymer chains by increasing their radius of gyration. Then the polymer mixtures were rapidly precipitated in the poor solvent, which contract the polymer chains by reducing their radius of gyration. This rapid collapse, polymer collapse, trapped the nanoparticles, preventing this microscopic phase separation. And we can see this nanoscale dispersion of the nanoparticles in this thermoplastic polyurethane matrix. And we choose the thermoplastic polyurethane matrix because of that its high elongation capability of the over the 600 and their thermoplastic poly properties. Due to the TPU's high flexibility, we could do the super twisting, stretching, and transform of the two-dimensional nanocomposite films to into the three-dimensional helical microrobot structures. And also applying the heat treatment, we could shape fixation of these helical structures after the twisting processes. And because of that lightweightness of these nanocomposite-based robots with a weight only 180 micrograms, it could be easily lifted along the direction of the magnetic flux generated from the two permanent magnets. When the two these permanent magnets rotate underneath the microrobots, the robots follow the direction of the rotating magnetic field. So there we can control the three multimodal actuation of the rotating, pivoting, and tumbling depending on the magnetic frequency of the rotating magnetic field. Particularly at a high frequency of the magnetic field, the robots can show the tumbling motions with a jump behavior, allowing them the rapid actuation and also adaptability in the obstacle environment, even though we did not additional control of the axis of the magnetic field. The rotation and revolution of the microrobots results from the force balance between the centrifugal force of the rotating magnetic robots and also magnetic centripetal force from the permanent magnets. So we can expect that their trajectory, because the orbital radius of the microrobots is determined by the robot body lengths and the magnetic frequencies based on this force balance equation. So we can tune their trajectory and the actuation mode by adjusting these factors. And for the collective behavior, these orbital maneuvers were achieved without the magnetic interruption interruption between the robots due to the high actuation speed up to the 60 body lengths per second for the tumbling motion case. Additionally, robots with the different aspect ratios experience varying centrifugal process, so enabling the independent multimodal actuation of these multiple magnetic robot systems. These robots even could demonstrate the collective swimming in the underwater at a really high speed actuation of the 56 body lengths per second. And using this high speed collective swimming behavior, we successfully demonstrate the nanoscale surface polishing of the vapor using the abrasive silicon nanoparticle solutions. However, for this high-speed actuation, steering stability is also really crucial. For example, automobiles usually use the onboard steering sensor to control their direction at a high speed. However, for the case of the miniaturized robots, the steering stability depends on their composite structure. Even in the blur-like environment, these microrobots show the adaptability to climb the obstacles. However, this non-uniform nanoparticle distribution may cause the negative impact on the robot performance by the non-uniform magnetization and the non-even the magnetic torque and force generation. So to compare the different nanoparticle mixing state, we implement the two nanocomposite processing to compare the distributed mixing of the nanoparticles. For this solvent evaporation case, because of nanoparticles can be easily aggregated due to their high interparticle interactions. So the increased diameter of the aggregated clusters are sedimented at the bottom of the nanocomposite films due to the high gravitational forces in the composite mixtures. When comparing the composite film by using the light transmitted films, we can observe the solvent evaporation films has reduced the transparency because of their increase the aggregated particle cluster size. When we check the cross section of the composite films, we could visualize the particle aggregation inside the nanocomposite films, particularly at a higher nanoparticle concentration. In contrast, with the nanoscale distribution of the nanoparticles, there was no macroscopic phase separation even at a high nanoparticle concentration of 58%. And this homogeneous mixing, the distributive and dispersive mixing were achieved by applying the rapid precipitation techniques. We can observe the evidence of the nanoscale particle distribution by analyzing the thermal stability of the composites when we compare the thermogravimetric analysis. This rapid precipitation case results in the peak convolution of the decomposition of polymers because of the nanoconfinement effect of the magnetic nanoparticles. Basically, thermoplastic polyurethane has two composition peaks. First one is that polyurethane bond dissociation in the hard segment, and the second one is that polyur decomposition in the soft segment. This hard segment and soft segment result in the phase separation of the polymer structures. However, when the nanoparticles were dispersed at a nanoscale and intermixed the hard segment with the soft segment, the hard segment decomposition was surpassed by the heat dissipation to the soft segment. Also, the phase separation and the nanoparticle aggregation affect to the robot morphology. We can see many microrobots inside the robots because the nanoparticle disaggregated nanoparticles hinder the polymer chain relaxation during the heat treatment for the shape fixation of the helical microrobot structures. However, for the case of the nanoscale distribution, there's no significant microvoid, and this microvoid and also the non-uniform magnetization profiles result in the cause the non-uniform magnetic torque, and with a tilted a variation in the center of the gravity of when they do the pivoting or tumbling behavior. So for the case of the solvent evaporation, these microrobots show the opposite pivoting or inward dragging and this non-uniform rotation behavior. That means that this study highlights the nanoparticle distribute mixing in the polymer and composite is essential for the stable with a high speed actuation. So, how about the application of the interactive motion of the multiple robots by surface coating of the microparticles onto the robot surface? Because they decrease the interparticle distance, we can get a higher magnetic attractive force between the robots, so we can control the magnetic assembly of the multiple robots. This assemble structure is for the vortex-induced cargo transportation. Previously, many grippers demonstrate the multi-cargo transportation for the precision control. However, these cargo numbers increase to the hundreds or thousands. It is difficult to simultaneous transportation, and it is time consuming. So we can think about that vortex generation, and by this vortex, cargo transportation is achieved by this collective swimming of the microrobots. When we generate the first vortex, the cargoes can be delivered into the inner space, and also around the first vortex, there are three vortex can drag the microbit. So when we generate the high vortex at the surface of the water, I was thinking that we could transfer the thousands of the multi-cargo by using the collective behavior. However, to generate like this high magnitude vortex, when I think about the material design, the most important thing is that low density rubber frame for the rapid actuation to generate the first vortex, and also simultaneously we need a stiff body by using the high modulus material with a three-dimensional rod structure to overcome the surface tension and overcome the drag forces. And to increase the first vortex, so we can make a high aspect ratio robot design with a large hydrodynamic volumes, and this can be increased by using the magnetic robot assembly. And when we control the inter-robot attraction or repulsion, this vortex can be manipulated through this collective behavior. The structure design was inspired by the human's musculoskeletal system. We use the rapid yet strong movement by using this lightweight and high Young's modulus bone. So we prepare this biomimetic nanocomposite structure by using the carbon nanotube yarn, which the high Young's modulus and with a lightness because of the nanoporosity. This is made of the twisting 100 carbon nanotube into the yarn, and the magnetic microparticles were coated onto the surface of the microrobot to the magnetic attraction. These microparticles could not be inside this nanoporous structure of the CNT yarn framework, and to selective surface coating of the magnetic particles, we applied the deep coating process of the polymer composites. Based on the phase transition of the thermocurable PDMS polymer resins, these microparticles could be bounded on the surface of the robot after the thermocuring processes. And these microrobots were actuated by the pulsed electromagnetic field. This is basically make a rotating magnetic field, and these robots can show the translational swimming motions along the magnetic field gradient, and it shows a really fast swimming behavior, maximum 180 baudillances per second. At the increased magnetic frequencies, the robots show the rotational swimming at the center because of the increased drag forces than the inertia force applied to the swimming robots. We can change the swimming mode even though we apply the multiple robotic system. At low frequencies, they show the assembled rectilinear translational swimming, and when we increase the magnetic frequencies to apply the rotational motions, the robots were assembled to the show the rotational swimming at the assembled structures. This is also basically from the force balance for the actuation mode control at a low frequencies. We can see that this rectilinear translational swimming with a high inertia and high magnetic attraction between the robots. However, when increasing the drag forces, the robots show the assembled rotational swimming or fluctuational rotational swimming because of the increased frictional forces applied to the multiple robots. We know that how to control the assembled structures, and we could manipulate the reconfigurable assembly of the collective robots. So that means we could control the vortex generation at low speed. We did not apply the high magnitude vortex, and increase the speed, we can generate the vortex significantly. So by using the vortex generation, we transport the thousands of the microbit at the surface of the water to transport inside this space or block this transported microbit by applying the rectilinear translational swimming. And also this block the microbits also released by changing the swimming mode. This is the collective behavior is show the importance of the use of the microrobot swarms, because a single robot cannot do alone. because they could not generate a high magnitude voltages. And also we can increase the coating thickness of the polymer composites onto the robot surface by the increase the viscous resistance through increase in the complex viscosity. When we increase the particle concentration during the decoding process, because of the there was a rheological calculation between the 20 and 30 volume percent. So we can see the drastic increase the coating thickness of this magnetic polymer composite onto the robot surface. So we can enhance the magnetization of the robots. This increase the robot magnetization can interact the magnetic field underneath the robot, so intensify the first vortex generation. So this high magnitude of the vortex generation, we could do the microplastic collection in the open space over the 4,000s of the microplastic collections. This is basically demonstrated by the rapid actuation of the assembled CNTY robots with the assembled rotational swinging. And we also can ask that these interactive motions can be controlled directionally. The anisotropic interactive motions can be inspired by the self-assembly of the magnetic particles. When we see the magnetic interactive energy, these magnetic particles assembled directionally with the direction of the petal direction applying to the along to the external magnetic field. Even though without the magnetic field, what if we control the magnetization inside the robot body? Previously, we used the soft magnet, which means that low co-speedy with a low residual magnetization. However, when we use this hot magnet showing the high co-speedy with the high residual magnetization, such as the neodymium microparticles, we can encode this magnetization direction inside the robot body. So depending on the magnetization direction, we can program the assembly configurations, and also this magnetic anisotropic property of the microrobots show the directional swarming behavior even at a dynamic state. However, to realize this multifunctional swarm intelligence, such as the obstacle overcoming, we need a high stiffness of the microrobot assemblies. Because the low stiffness of the microrobot assembly can be easily disassembled and it could not achieve this kind of complex task. So we designed we choose the high elastic modulus material of the epoxy for the high structural stiffness. The epoxy polymer has a high close linking density and high glass transition temperature, so it results in this high mechanical property with a Young's modulus of the 5 gigapascals. And also this directional assembly can be enhanced by the magnetization profiles, and also this structural assembly is increased by using the cuboid geometry of the microrobots, because the spherical robots are usually assembled through the point-to-point contact. But when we use the two-dimensional interface between the microrobots, I was thinking that we increase the assembly structure of the microrobots. And also, the magnetization profile control is important for the uniform swarming behavior, because when we did not apply the uniform magnetization, the robots show the random interactive communication each other, so that result in the out of control swarming behavior. However, when we apply the uniform magnetization profiles in the microrobots, that is capable of the this kind of uniform assembled rotation when we apply the rotating magnetic field. So we need uniformly magnetized microrobots. However, how we can obtain these microrobots with the mass production? So we prepare the microrobots by the replica molding, using the microarray with a composite of the 100 of the microrobot structure in a single master array, and we apply the in situ magnetization to encode the magnetization profiles. After the hot magnetic particles disperse in the epoxy precursors, and we replicated this structure, and also by applying the thermal curing for the robot preparation, and also we apply the magnetization profiles at the higher co-speedy magnetic field. Then we can obtain the 100 of the microrobots in simultaneously using a single microarray mold. The reason why we program this magnetization profile is that each assembly has the other preferred functions for the swarm behavior. The first one is that head-to-tail assembly of the microrobots, and it has a feature of the highest assembly length, and also, in the other hand, the face-to-face assembly of the microrobots show the highest contact area. The volume ratio makes the highest structural stiffness during their swarming behavior. And this slip co-facial assembly of the multiple robots results in the interconnection point through the magnetic attraction, and it makes the highest backing density of the swarm behavior. Each swarm of the multiple robots show the other functions. First, for the highest aspect ratio case, these microrobots can pivot to climb the obstacles autonomously. Because of the making assembly structures, they could climb, and also meanwhile, this structure has a lowest assembled stiffness, so at the increased magnetic field, the higher centrifugal force applied to the end of the assembly, the microrobots can be easily disassembled due to the high centrifugal forces. So these robots disassemble, and self-drawing behavior can be, we consider this behavior. And last one is that this high aspect ratio assemblies can lift the obstacles by going inside the obstacles, and this lifting capability is maximized by using the high aspect ratio assembly, because they can generate collective lifting forces, upward forces applied to the obstacles. Meanwhile, when we apply this slip co-facial assembly with the highest packing density, and these assemblies can show the raft-like interconnected assembly at the surface of the water. So by using that features, we could transport the heavy drug at the air-water interface rapidly for the rapid drug deliveries. And also, these high packing density assemblies can generate the high elastic energy transfer to transport the heavy conductive indium chunk to connect the wire or disconnect the wire on demand when we want to do that. So this high packing density assemblies is high potential to transport the small scale cargos in the when human could not control that. Meanwhile, when we apply the extremely high speed actuation above the 80-100 millimeter per second, this structure can be lose the structure stability. However, when we use the face-to-face assemblies, it has a maximum inter-robot connection, so they demonstrate a stable assembled structure, and they could generate the high impact force to manipulation of the high surface tension material like liquid metal manipulation. This high structure stiffness assemblies can transport the liquid metal and also shape morphing into the spherical shapes and the other functions like cleavage of the liquid metal. They achieve these manipulations. And also based on the high impact force of the swarming behavior, these robot swarms demonstrate the impurity in the tube when we biomimetic this vesicular-like collision. So they show the potential for the microsurgery for the blood clogging phenomena. And lastly, when we choose the prefer the swarming of the multiple robot assemblies, we can do the organism control, and for the small scale organism, we need a lower shear force applied to this organism, because high shear forces can injure this object. So we apply the high packing density assembly to transport the organism, yet but they do not injure by this swarming behavior. And for the case of the increases in the body length, for example, from this superworm, we can apply the high structural stiffness assembly to prevent their direction of the to go to the feeding site. And when we stop this rapid actuation behavior, this superworm can get a feed on demand behave by the on demand manipulations. In summary, to realize microrobot swarm intelligence and control the interactive and independent motion of these microrobot swarms, I did I prepared a programmable polymer composites by the structure property relationship investigation to optimize this performance of the robot behavior and on-demand multimodal swarm behavior, and also with a high-speed actuation with the steering stability. And this work we collaborate. This is my collaborators for my project, and now I'm studying on the medical application of the micro size and nano size robots at CalTech. And thank you for listening my talk, and feel free to ask questions.
Sukyoung, thank you very much. This is a brilliant presentation, and I think this is really inspiring work that you're showing here. In particular, that you control everything about those micro robots from the manufacturing process, all the clever ideas actually to get the 3D packed in order to enable these motions, and then up to the ideas how you can actually control them and make them move in ways that they're actually conducting really useful things. It's absolutely fascinating work.
Thank you so much.
I think this is really, really cool. And when people talk about robots, they often talk, about robotic arms and things like that, and also inverse kinematics and so on. But you actually achieve this by designing the actual body, and it's super cool. And and then when you control them, the circular motions, like I think on slide 11 you show it for the first time, that they actually move in a circle. You had this a couple of times. In order to achieve that, you also need a rotating magnetic field, right?
Yes, it is.
And this is then induced by an electromagnetic field, by a magnet that you can essentially realign or turn on and off by electromagnets, or essentially RF pulses.
We apply the polymer-magnetic, but this is depending on the robot actuation.
This one, here on the left, that's the same.
Yeah. You mean that one?
Yeah, and this is at a fixed rate, and this induces the robot motion in the circle, right?
Yes, it is. This is induced by the rotation of the permanent magnet, not use the electromagnetic coil system, because of the the permanent magnet, and they rotate at the below of the microrobots, and because of the rotating magnetic field of the permanent magnet, the magnetic robots also rotate and also follow the permanent magnet with the direction of the magnetic flux. I can show you the presentation again.
But just because when you talk about magnets, it's very important to understand in which direction they're applied and so on.
Yes, it is. Yeah.
So you have the essentially the rotating magnet underneath that is introducing the circular motion.
Yeah.
This is super cool, and also that you're now working on essentially medical applications and drug delivery. There have been quite a few works where you had magnetic nanoparticles, and then also essentially manufactured in a way that they had a drug associated to the nanoparticle, and then you could steer them essentially to focus on a specific site.
Yes,
and I think a big problem that they have is that I think a lot of the particles, they kind of get stuck. They don't arrive at the location. But with the tumbling motion that you show, I think the amount of particles that will get stuck somewhere can be much controlled.
Yeah, because they just because they can lift obstacles. So when there are some obstacles, like a winkle shapes, they can climb even though by changing the direction of the magnetic field.
Yeah.
Yes.
Because this is a big challenge that they typically have, and with your approach, you solve the challenge. There's also larger robots the capsule endoscope. So this is it's like a rather big. It's like a pill more or less, and it has a tiny camera.
Yes. Yeah.
It also has a battery because it records a movie. Yeah? And you, instead of putting an endoscope down the throat, you will swallow the pill. And these capsules, they get lost in the intestines quite frequently, which is one of the reasons why they never made it into a medical product or into the market. But with being able to control the locomotion better, I think that could be a total game changer for many applications. That you can also make them swim. I mean, it's a long way, but this is really
right. Yeah.
If I see that, I get a lot of interesting ideas from just being able to do that. It's absolutely fascinating.
Thank you.
One thing with the particles, how do they? I assume because they're moving, do they get damaged over time? Do they wear off, or did you ever encounter problems that after certain million times of tumbling motions that the particles get damaged?
No, they did not get any damage, even though we applied over 1 week, or we did not check the time variation, but because of we use the polymer composites, so they have a structure, do not get any damages, even though they face the obstacles or the other things below the below the materials mechanical properties is below than this polymer composites.
And essentially, then you would also need excessively high magnetic force fields such that you would cause damage to the particles, right? They won't break or untwist or do stuff like that.
But I think that it did not damage for the applying the magnetic field, or even though with a high magnetic field gradient. I mean that it can disassemble or make a motion, out of control motions when we apply the really high magnetic field gradient. However, I think the shape of the microrobots did not change by the magnetic application. However, when we use the same morphable structure by using the low Young's modulus polymer composite, they can easily show the deformation, and it can be more can be changed by the it can be changed depending on the magnetic field conditions.
So they essentially get flexible then, or
yeah, but in this case, the robots did not show the any shape deformation because I want to design the more high assembly stiffness between the robots. So I did not consider the deformation for the robot design.
So when they get too close, they start assembling. And if you want to break the assembly, you essentially increase the magnetic force. That's
right.
Key to disassemble them.
Yes,
it's so cool. it's really cool. Also the many on slide 39, I think you showed that you are able to control the drag, and there's a question. How do you adjust that? Is that using a different fluid, or the robot geometry? So or is it the magnetic field that you can adjust the drag with?
Your question is that the other fluid can be applied, or
No, in slide 39, there you had different drags, and it's a question how you can control the drag.
Okay, let me see. Yeah. The drag is basically, as you mentioned, we can change the magnetic frequencies, and also this is just a first balance between the magnetic attraction and drag. So when we increase the particle concentration at the surface of the robot body, that means that we can increase the magnetic attraction that it makes the higher attractive force than these frictional forces. So we did not change the drag forces, but we changed the magnetic attractive force applied to the robots by increasing the particle concentration on the surface of the robot body, or dispersion concentration in the robot body.
I see. So these are then different robots that we are seeing, and different forces, both.
Yes, this is just a representative the videos, but even though when we use the apply the same condition of the this particle concentrations, when we change the aspect ratio of the robots, or when we change the rotational frequencies, that makes the different drag forces applied to robots, so we can design the switching of the swimming behavior.
I see. Sukyoung, this is a fantastic work, fantastic presentation.
Thank you again.
Absolutely thrilled by this. And thank you very much for doing all the effort of the online presentation and everything. And yeah, thank you for the brilliant presentation.
Thank you for listening to my talk.